Hi students, this is Mrs. Foy, and this is a screencast on the Extinction Vortex. Sounds kind of ominous just in its name, but in reality, extinction is part of the natural flow of life. What is interesting about extinction is that we can look at extinctions in the past, and that can help us predict what is happening in the future. So there is a background extinction rate. There are always species who are going extinct. I think this is an interesting fact here. Species longevities range from 2 to 10 million years. So about 4 million years on Earth is the average of species before they go extinct. Marine invertebrates, 2 to 5 families are lost every million years. And of course, we have to realize that when we're looking in the past, we are limited by the organisms that can actually be fossilized. They're what we see in the fossil record. And so we can see species in the fossil record appear and disappear, and that gives us a clue about what has happened in the past. When we look at our geological history, we can see that there are 5 mass extinction events, and we can see them here that are listed for us, where the extinction rate peaked much higher than the normal background extinction rate that's leveling off about this level. So this Cretaceous tertiary extinction is the extinction that took care of the dinosaurs. And that was just 65.5 million years ago. This Permian extinction wiped out, I think it was like 90% of marine life. So we have had some mass extinction events in the past. What is interesting is that many scientists think that we are actually at the beginning of a 6th mass extinction. And what's going to be different about this one is that this one is actually caused by the human population. So we do have, as I said before, a background extinction rate. But what is happening, as you can see here, is that the extinction rate is accelerating past what the normal background extinction rate would be. This is a projection from the United States Geological Survey, and it is projecting that as we go forward in the next 100 years, that the extinction rate will continue to skyrocket along with the human population growth. This is an article from the National Science Foundation. And it is basically talking about the fact that if you are just looking especially at large mammals, then we definitely see an extinction rate that is much higher than what we would expect. And we can point the blame at 2 very specific things. One is climate change. We see specifically with amphibians here, where this diagram is showing, is that the increased global temperatures actually favored a certain type of fungus, and that those fungal infections, we know, have been devastating for populations of amphibians. We know amphibians are kind of the canary in the coal mine about extinctions, and so we look to what's happening with amphibians. They have because they breathe with lungs but also through their skin, they have a greater surface area that can be impacted by environmental toxins, and that's one of the reasons why they are so vulnerable. So, what causes extinctions? Well, one of the things that we know is that there are an awful lot of human causes. The destruction and loss of habitat is number 1. Overharvesting, overhunting, invasive species, again, these are both from human impacts. Pollution, and of course climate change. Climate change is going to alter the living conditions for these organisms, which may lead to their demise. Here we have one of the very endangered species on the brink of extinction, one of the species of rhinoceros that are being actually guarded by armed guards because there is a market, unfortunately, for their horns. They are believed to be aphrodisiacs, and so people have been butchering the animals to get the horns. And so there are some countries in Africa who are actually have an armed guard escort for these rhinos to try to keep them from becoming extinct. So what is it that makes some species susceptible to extinction, like the rhinoceros that we saw? And one of the things that is the most susceptible thing about species going extinct is if they have a small population size. So rare species that have a smaller number of individuals are the most at risk. And what happens when a population gets very small is that there is a loss of genetic diversity. And remember that your gene pool is kind of like your toolkit. You don't know what's going to happen in the environment. You don't know what stresses you're going to be exposed to in the survival of life. So the variety in your gene pool is something that is advantageous for your population. And there are sometimes changes in this gene pool, both the frequency of the genes and the loss of diversity, that's called genetic drift. So there are two types of genetic drift that we can talk about, that we can see happening in populations. One of them is called the bottleneck effect. And for example, we see this happen in elephant seals. So if you have individuals that die as some type of cataclysmic event, like overhunting, which is what happened with the elephant seals, or some kind of disease, that all of a sudden you have a very sudden decrease in your gene pool that is going to affect the genetic diversity of that population in the future. Another example is something called the founder effect. The founder effect is when a random event happens to isolate a smaller population of the mother population, and just by chance that smaller population has a difference. They may have lost genes, or genes that are more a dangerous gene that just might happen to be in their population becomes more concentrated, so to speak. So this happened, for example, with the Afrikaners that came to the white Dutch settlers that came to South Africa, just by chance had a higher concentration of a devastating genetic disease called Huntington's disease. And so the descendants of that population now has a much greater chance of Huntington's disease than would the normal population. So here's an example of one type of genetic drift, this bottleneck effect. This cartoon is showing you that if you have just a few individuals that happen to survive, then you only have these little beads here are supposed to be symbolizing the gene pool. And if you have fewer individuals, then you can see that my original parent population had a lot more yellow beads. And just by chance, because of whatever event happened, so some kind of disease or overhunting, or some type of earthquake or whatever that got the population very slow, just by chance I had more blue genes than the yellow genes, and so my future generations are going to have differences in the population of those genes. The founder effect can be seen from this cartoon, that over here you can see that I had a population of yellow and red ladybugs, and just by chance one of them gets blown to this island. This a lot of times happens in island ecosystems. And because it was a red ladybug, I don't have the yellow ones. Those yellow genes were lost just by chance. And so now I have less genetic diversity, which is going to make those populations more at risk. So what happens when population sizes get very small? So one of the things that we just saw was genetic drift. So you've got random loss of genetic diversity, and that's just based on who survives and their offspring. The other thing that happens when populations get very small is that there's no one to breed with. And so we have inbreeding occur, where we have organisms that are related, so they have less genetic diversity, and that just furthers the problem of even less genetic diversity. It makes them vulnerable. So this sets off a chain, kind of a positive feedback reaction of something called the Extinction Vortex. And this is the sequence of what happens. So you have this small population where inbreeding can occur, and just random genetic drift can occur. And that results in the loss of genetic variability. And remember that our genetic variability is what is our toolkit for survival in this struggle to survive. So because we have less genetic variability, now we have a reduction in the individual fitness and in the population adaptability. So what does that mean? So that means I have less genetic tools in my toolkit. So if some catastrophe happens in my environment, I have less tools with which to respond to that. Now, I'm not talking about an individual, I'm talking about a population. So now what is happening is that because of that loss of genetic variability, I have a lower reproduction rate and a higher mortality. So we can see this, for example, in populations of leopards. Leopards are very close to extinction, as are many of the big cat species on Earth today. And we are having a very difficult time trying to increase their genetic pool. They have very low reproduction rates, especially in captivity, as is what happens with a lot of these organisms. They have a higher mortality. There's a lot of inbreeding in the leopard gene pool. And so this makes the individuals less likely to survive. And so what happens is a smaller population. And that smaller population then starts that positive feedback loop, which we call the extinction vortex. And at some point, there is the point of no return, and then there is nowhere to go. There's not enough individuals left to be able to sustain the population, and extinction will occur. So the one thing I'd like to end on is that the article that I spoke of earlier from the National Science Foundation talks about the fact that, this is not without hope. We are humans that have some control over our actions. And if we make concerted efforts to do things like stop invasive species, stop the loss of habitat, protect organisms, our populations that are at risk, and use our ingenuity to try to prop up these populations, then perhaps we can stem off a sixth mass extinction. I certainly hope so. Thanks so much. Talk to you later in class.